To continue our discussion of polar equations, we're going to look at symmetry. Now, we've seen symmetry with respect to rectangular equations in the past. We've dealt particularly with functions quite a bit, dealing with even and odd functions and how they are symmetric with respect to the y-axis and origin, respectively. And also, we've seen some x-axis symmetry as well with other relations that are not functions. And now we're going to be able to take a look at the polar form of that symmetry and what it looks like. So just a quick review, if you recall, with rectangular coordinates, to be rectangular with respect to the x-axis, to be symmetric with respect to the x-axis in rectangular form, you would have a point, xy, on the graph. Then there must be a symmetric point with respect to the x-axis, right? So you would have to go perpendicular to the x-axis and the same distance away from the x-axis. Now that coordinate, or the coordinate of that point, they'd have the same x-coordinate, but the y value would be negative now, okay? So you'd have x comma negative y. And that's true no matter how the graph is designed. Whatever point is above the axis would have to have a symmetric point below, and whatever point is below would have a symmetric point above. So this combination of xy and x negative y, they must both be on the graph to have x-axis symmetry, which, if you follow that through, if you were to replace y with negative y, and simplify, you'll get exactly the same equation, okay? So replacing y with negative y, you will get the exact same equation. Now with the with the y-axis, if you have the point xy and you reflect it across the y-axis, again the same distance across, it's the x value that changes sign, and the y value stays the same. The height stays the same, but now the horizontal distance or value changes sign. And so you would replace x with negative x, and after simplifying, you should again get an identical equation. This is how we worked with even functions, right? If you replaced x with negative x, so f of negative x should equal f of x, right? The equation should be the same whether you put in negative x or positive x. And so that's how we did the even functions, or the y-axis symmetry. For origin symmetry, then you would be reflecting both coordinates. It would have to come through, and if I kind of sketch this all out, these probably aren't very parallel to each other, but you somewhere down here you get a point that is again equal distance across the origin. It ends up changing sign on both variables, and so you would have you would replace x and y with negative x and negative y. So if you replaced both variables with their opposites and then simplify, you should get the same equation. And so here in function notation, you would say f of negative x is negative f of x. And so the negative input results in a negative output, right? Negative input, negative output. Or the opposite, I should say, because you could have, a point that's negative and positive, and the opposite sign input will give you the opposite sign output. So you could have origin symmetry going from the second to fourth quadrants too. They don't have to both be positive or both negative. They can be different sign. Okay, so that gives you the rectangular idea. But now we look at the polar equivalent. Let's erase some of this stuff here, just to clean the graph up a bit. So now we're not going to be looking at x's and y's, except for the axes. We're going to be looking at our theta coordinates, okay? So instead of xy, it's going to be r theta. Well, if you consider a point that has r theta coordinates to be symmetric with respect to the x-axis, the radius would be the same. So you get r to be the same, but now instead of going theta in the counterclockwise direction, you'd be going theta in the clockwise direction. So we'd be looking at negative theta, right? Different direction, same angle. So if you have r comma theta, then r comma negative theta would also have to be on the graph. And it doesn't matter where that angle is. If that angle is over here, then the negative angle would be down. So it just, the symmetry will hold as long as you replace theta with negative theta. And that's for x-axis symmetry. So we would replace theta with negative theta. And again, after simplifying, you should be able to come up with the exact same original equation. With y-axis symmetry, think about how you would get the symmetric point over here on the other side. Well, again, your radius is the same in theory. But now, instead of doing negative theta, you'd have to add pi to that, or 180 degrees, right? So it's negative theta plus pi will get you the other angle. Now, usually we would write that instead of negative theta plus pi, we might write pi minus theta. Okay, so for the y-axis symmetry, you would replace theta with pi minus theta. And pi minus theta would give you, or I guess after simplifying with this angle, you should get the equation from the original theta angle, okay? Again, you'll probably have to use some trig identities to make this simplification work out, maybe a sum or difference identity for a cosine or a sine or something like that. And eventually some things would cancel out and you get the same equation. Yeah, for polar, there are actually two options. Because with polar, you're going through the pole, you're going into the opposite quadrant here. It's not a very good straight line, something like that. And so what happens over in this other quadrant is that you have the same radius but in the opposite direction. So one way that you can show polar symmetry is to replace r with negative r, but fixing theta, okay? So option number one is to fix theta and replace r with negative r, right? We've seen that radius can be negative for polar coordinates. We do allow for that to happen. So if you fix a 30-degree angle and have a radius of 5, then its symmetric point would be a 30-degree angle with a radius of negative 5. The other way to do that is to fix the radius and say that it's 5 and just add pi to the angle, okay, or replace the angle with theta plus pi. So option number 2 is to fix r, fix r and replace theta with pi plus theta. So you add 180 to the theta to get the symmetric point. And again, that's true for any point on the plane. And if you do that, if you fix the r and replace theta with pi plus theta, you should again get the exact same equation that you started out with. So either of these options will work, and sometimes you'll find that one will work better than the other. Sometimes fixing theta and working with r is a little bit easier because the trig identities might be very difficult if you tried this route. Whereas sometimes this route will work better because maybe you've got too many terms with r to mess with, and there's a simple trig identity that will help us out with this one. So it just depends on the situation, the equation that you're working with. A real quick example of this we just saw, in the previous video, you saw an example where we shifted a circle, to the right 2 units, and it had a radius of 2. And the resulting the resulting rectangular equation was x minus 2 squared plus y squared equals 4. And the resulting polar equation was r equals 4 cos theta. I believe that was it. Yeah, 4 cos theta. And so in this example, if I were to do check for some of these symmetries, obviously this circle has symmetry with respect to the x-axis only. It does not have symmetry with respect to the y-axis or the pole or the origin. Just double checking something here before I move on. Yep, that's right. And so we could check for x-axis symmetry simply by replacing theta with negative theta in the polar form. If I do that, r equals 4 cosine of negative theta. Well, how do I try to figure this out to where it goes back to the original? Well, we do have an even-odd identity. It's one of our fundamental identities from trigonometry that says that the cosine of any angle is equal to the cosine of the negative angle. And that's because the cosine is an even function, right? It has y-axis symmetry. Cosine x is even function, okay? And so, if you looked at the graph of the cosine, you know that it has the y-axis symmetry. And so these two things are exactly the same, so I can actually replace. And it doesn't look like I did any work really, but I did use this even identity. So we'd say by the even identity for cosine. So by the even identity for cosine, we're able to show that the equation with the negative theta is exactly the same as the equation with the theta in it, and so therefore we have x-axis symmetry. And of course, if I tried to repeat this process with any of the other symmetries, it will not work out. I could do that with the y-axis symmetry. I could replace, and this will take a moment to work this out. Oops. Because we're going to need some trig identities, but we could take r equals 4 cos theta. We could replace theta with pi minus theta. Remember, that's how you would determine y-axis symmetry. And then probably the easiest thing to do is to use our difference formula for the cosine line, which if I were to write that out, the cosine of, if you think of this as alpha minus beta, or x minus y, whatever, the difference formula is cosine of the first angle times the cosine of the second angle, plus the sine of the first angle times the sine of the second angle, okay? And now if you were to evaluate the two angles with the, or the two trig functions with the theta, with the pi, the cosine of pi is, I think that one out, that's -1, right? Cosine pi is -1. And the sine of pi, think about the sine of pi. Pi happens halfway across the wavelength, so that's at 0. So this guy here is 0. That one's -1. And so I end up with r equals -1 times 4, -4 cosine theta. Well, -4 cosine theta and 4 cosine theta not the same function, not the same equation. And because they're not the same equation, I don't have the y-axis symmetry. So that is not equal to 4 cosine theta, so no y-axis symmetry. Okay, and then of course I could repeat this for the pole. And again, there's two alternatives to this. If I do the r with the negative r, it's going to be very obvious. We're going to end up with this exact same equation, right? If I plug a negative r in here, divide both sides by -1, I get back to this, which is not the original. So I'll skip going through that. And of course, if I did pi plus theta, I'd again use the the sum formula. So maybe I'll run through that one, because that one's not as obvious. So if I replace, oops, that's not what I want to do. If I replace the original theta with pi plus theta, then I use the sum formula, which is the cosine of the first angle times the cosine of the second angle minus the sine of the first times the sine of the second. Again, your cosine of theta, cosine of pi is equal to -1 again. The sine of pi is also 0 again. So it really doesn't change a whole lot except for the sign in the middle, which, because you're adding or subtracting 0, doesn't change. So we still end up with r equals -4 cosine theta, which again, we've seen now a couple times that that is not equal to the original, so there's no polar symmetry. Or symmetry with respect to the pole is probably a better way to write that, okay? All right, so anyway, that was just a quick example, and it shows you how you can work with all of these different types of symmetries with a polar equation.